Hi everybody, and welcome back to my lecture series on hardware for deep learning. I'm Dr. Adam Teman of the EnICS labs at Bar-Ilan University. Today we're going to do part 2, Convolutional Neural Networks. Today's lecture has 5 parts: Introduction to Convolutional Neural Networks, Convolutional Neural Network Basics, the size of a CNN, additional CNN components, and famous CNNs. This video will cover the first 3, and the next video will cover the second 2 sections. So let's start with an introduction to CNNs, to convolutional neural networks. So remember that we have this explosion in fully connected dynamic neural networks. Beep. So remember, we have this explosion in fully connected deep neural networks. So fully connected layers have a synapse connecting each neuron in one layer to every neuron in the following layer. So we see that this neuron is connected to all of these neurons, right? So if we have one layer that has m neurons and a second layer that has n neurons, we get a huge number of weights, m by n weights in each layer. So this layer has m times n weights, which becomes a huge number. It results in huge storage and huge computation requirements because we have to multiply in each one of those. So instead of that, we take the convolutional approach. Convolutional neural networks relax the requirements. This is lightly inspired by the visual cortex, where cortical neurons respond only to stimuli in the receptive field. So basically, we're going to only look at the receptive field and not look at the entire image or the entire input at once. So these CNNs, also called ConvNets, they're basically sparsely connected neural networks. How do they become sparsely connected? By employing weight sharing. So here what we have is an input map that is size h by w. Okay, and instead of looking at the entire h by w at one time, we take a smaller window. For example, this filter, which is only size r by s. Okay, and r by s are small. Okay, that way when we take this and we convolve it with a certain part of the input map, we get many fewer operations per producing each output, and we get significantly fewer weights. So let's describe how this is going to work a bit later on. This was actually introduced by Jan LeCun and Yoshua Bengio, 2 of the 3 guys, along with Geoffrey Hinton, that were awarded the Turing Award for their work in artificial intelligence last year. And they introduced a network called LeNet. This is the original convolutional neural network in a paper called Gradient-Based Learning Applied to Document Recognition. Okay, this was already done in 1998. We're talking a long time before AlexNet came out, a long time ago. And as you can see here, they introduced a network that could take these handwritten grayscale images and go through these convolutional networks until it came out with an output that would classify them. This was actually used already, deployed in ATMs to recognize digits for check deposits. We'll discuss LeNet later on a bit in more depth. But the big breakthrough came in 2012 by this guy, Alex Krzyzewski. He was in Geoffrey Hinton's group, and he wrote a paper called ImageNet Classification with Deep Convolutional Neural Networks. Okay, this was the winner of the ImageNet challenge in 2012, and you see that again this has these convolutional networks, which we'll discuss in depth, and we'll actually discuss AlexNet in depth toward the end of the lecture. But it was very deep. It had a lot of layers, and you will see that it had a lot of parameters. What AlexNet did and why it was such a breakthrough, you can see in this ImageNet challenge. So ImageNet challenge was introduced in 2010, and you see here the error rate. So the error rate in 2010 was 28%, and it went down to 25% in 2011. These were using traditional image recognition algorithms and methods. AlexNet came in 2012 and blew the field away. It got almost a 10% gain over what the last year had brought in. AlexNet was already a deep network. It already had 8 layers, and it used all kinds of things like GPUs to train it. And we'll discuss again AlexNet later. But you can see in the yellow line here is the growth of the number of layers actually used to win the ImageNet challenge. And you see that the accuracy kept improving. through 2013, 2014, VGG came, and GoogleNet came. In 2015 was another breakthrough when ResNet came, and it beat the human level accuracy. So the human level accuracy, well, I didn't draw that exactly correctly, but it's about 5%, and that was, according to lore at least, by Andrei Karpathy sitting there and actually doing what these networks do by trying to recognize what was in different pictures. So actually nowadays the standard ImageNet challenge is not as relevant, because since we already passed human level accuracy and we do get some incremental increase maybe in what newer networks can do, we're already good enough. So there are other challenges that are more interesting and bigger targets than the just image recognition one. Okay, so saying that with a background, we'll go into the basics of convolutional networks. So what is a convolutional layer? So let's say we have a 32 by 32 by 3 image. We showed before that in CIFAR 10 we have this type of a thing, a 32 pixels by 32 pixels, and it's RGB. So we have 3 of these two-dimensional planes, and we take a filter, and the filter here is smaller, so it's only 5 by 5, and it also has 3 dimensions. Okay, so what we're going to do is we're going to convolve the filter with the image, which means we're going to slide over the image spatially computing dot product. So we're going to take this filter, we're going to start over here and then move it and then move it, and we're going to slide it through the whole image and then go down a pixel and put it over here and slide it this way and then go down and slide it this way. And each time we put the image on one part of the 2D input, we're going to multiply and accumulate all of these values that are inside. That's what convolving is. And each one of these times that we slide it into a certain area, we're going to get an output. Okay, so some nomenclature here. The input to a certain layer is called an input feature map or an IF map. Okay, and each of the values there are called input activations. So this could be called an input activation matrix or tensor as well. Okay, the number of 2D feature maps that we have at the input, that is called the number of channels. So in this case, we have 3 channels in our input. And the filter over here, we called it a filter, can also be called a kernel. It can also be called a weight matrix, because each of these things is a weight. Okay? And one thing that we need to pay attention to is that we need to, if we take and look at one of these 2D input feature maps, we need to convolve it with a 2D filter. But since we have three of these input filter maps, we have a depth of 3, we need to have 3 of these filters. So the size of the image, the depth of the image, and the depth of the filter will always be the same. So again, looking at our convolutional layer, again, we put our 3 filters on top of our 3 input feature maps here somewhere. And what we're going to do is we're going to do this dot product. So each of these 5 numbers by 5 numbers is going to multiply by 5 numbers by 5 numbers in at some point in the in one of the planes of the input. And since we have 3 of them, we're going to have a total of 75 numbers, multiplying 75 numbers and accumulating them, and the result will be one single number. That is the dot product between the entire filter and the entire area that we're at right now on the input feature map. Okay, that's doing this operation. We have to add the bias as well to that. So there's going to be one bias over there. Now, just looking at this, you can see something interesting. What we have here, if we took a 32 by 32 input image and we used a 5 by 5 filter, we only get a 28 by 28 with 1 depth output, and we'll discuss that in a bit. The output we also call an output feature map, or it's a matrix of output activations. So each of these guys is going to also go through an activation, which we're going to discuss in a little bit. And so these are called output activations, each of the things in the output feature map. So what about multiple filters? So as we said before, each filter has the same depth as the input feature map. So if our input was 32 by 32 by 3, that means the depth was 3. We said before that the filter size has to be the same depth, so it also has to be by 3. So for example, in our example, it was 5 by 5 by 3. But there can be mini filters. There usually will be mini filters, and it's one of the hyperparameters we actually play around with is how many filters we have in each layer. Okay, so each filter will result in another separate activation map. Another separate two-dimensional output layer will be made by every filter we have, and this will be the channel depth of the next input layer. Okay, so let's look at an example. We have our 32 by 32 by 3 input, and what that means is we have, again, a filter of 5 by 5 by 3. So each filter we make will create one of these two-dimensional outputs, but we can take 6 of these, and then we'll get 6 output feature maps. And then when we go into the next layer, our input depth will be 6. Okay, so given 6 filters, we get 6 image maps, and the input to the next layer is now going to be 28 by 28 by 6. So what is a basic CNN? A basic CNN is a sequence of convolutional layers, which we just showed now, interspersed with what we call activation functions, which, as we discussed before, provide the nonlinearity. So we have this type of an input map. We do a layer where we do convolutions, and then we apply some sort of activation, for example, a ReLU. In this case, we used 6 filters that were each 5 by 5 by 3. 3 is this. So we got 28 by 28 by 6. That's the depth because we used 6 filters. Okay, and these are all activations because they went through convolution and then ReLU, or again the activation function. Okay, after that we can again do some convolution and again ReLU. For example, this time we're going to have 10 filters in this level. That means that our next layer is going to have a depth of 10. Remember that each of these filters had to have a depth of 6 because it has to be matching what we had at the input. So then we can continue with convolutions and ReLUs and so forth. So what are these activation functions? Okay, so the classic kind of activation function was what we called the sigmoid. Okay, and the sigmoid looks like this. It starts at minus infinity and goes to plus infinity, going from 0 to 1 on the y-axis, and it's a nice smooth type of thing that we can differentiate and so forth. And that was generally the activation function that was used. The problem with sigmoid is that it is not centered around 0, and being not centered around 0, it causes ugly distributions sometimes, and it's harder to train. So that's why hyperbolic tangent became kind of popular, which is very similar to the sigmoid, but instead of going from 0 to 1, it goes from minus 1 to 1, and that means it is centered around 0. However, with AlexNet, the rectified linear unit was introduced, and the rectified linear unit is a very, very simple function. So it's the max of 0 and x. In other words, every input that's negative will output a 0, and every input that's positive will just output itself. And that's very simple to calculate, and it causes a lot of sparsity. It has a lot of good characteristics, but it is not centered around 0, which we said is not good. And it also is a kind of a strange thing, which is hard to understand why it works, but the bottom line is that it does. One of the problems with it, it tends to kill gradients because of this 0 that happens below for negative inputs. So different things have been tried to correct or improve on that. One of them is the leaky ReLU. So instead of having a 0 output when we get negative numbers, we have a very small gradient that's output. And another thing is the exponential LU, which is trying to give some sort of exponent here for negative numbers. However, in the bottom line is that while these theoretically should probably work better, they're more complicated, and the ReLU seems to provide better results. So that's generally what is used nowadays in at least image recognition is ReLU. Some of the other ones are used in different types of networks. So going from CNN basics, now we'll go and look at the size of a CNN and see how much actual computation and storage we'll need for one of these guys. So let's start with the output of a convolutional layer. So we have this 7 by 7 by 1 input just for the example, and we have a 3 by 3 by 1 filter. So what we do for the convolution is we take our filter and we put it on the input, and we do a dot product. So each of these green guys is multiplied by the inputs. So they have this plus 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 this. Sum that up, and we get one output over here. Okay, so we did 9 multiplications and additions, 9 max, and we got one output. Then we slide the window over. We do another of those 9 multiplications and additions, and we get the second output over here. We continue and slide again and again and again until we get to the end of the window, and we got a row of a total of 5 of these pixels. Okay, now that we finished that, we can go down a row, and we do again these convolutions, and then we move down a row, and finally, if we move down all the rows, what we see is we're going to get a 5 by 5 activation map. So we started with 7 by 7, and we got 5 by 5. Why did we lose the edges? Because this first filter was sitting over here, and it was focusing basically on this pixel rather than focusing on this pixel. And the last filter was sitting over here, and it was focusing on this pixel rather than this pixel. So we lose a pixel in each of these directions, and that's why we get, instead of 7 by 7, we get a 5 by 5 activation map. So we may be losing some of the information there. So what is commonly done is what's known as padding by zeros. We don't use this 7 by 7 by 1 input, but we'll actually put an extra 0 around the border, and that will give us a 9 by 9 by 1 input. But these don't add information, they just allow us to focus on these extremes. So let's see how that works. We put our 3 by 3 filter over there, and then we convolve and convolve and convolve. And finally, if we go through the whole thing, we get this 7 by 7 by 1 activation map. So we didn't reduce the size of the activation map by going down. Now, in our original example, we had a 32 by 32 by 1, by 32 by 32 by 3 input image, and our output was 28 by 28 by whatever. Why did we lose extra pixels? Because we were using a 5 by 5 filter. And if our filter was 5 by 5, that means that when we put our 5 by 5 filter over here on our original guy, there's our 5 by 5. Okay, our first pixel focused is over here. So we lose 2 in every direction. Okay, and that's why if we lose 2 in every direction, our last filter will be down here, right? Oh, I missed one. I meant like that. Okay, that means we were focusing on this. So we missed 2 in this direction too. So we actually lost a total of 4 pixels. So in this case, we would need to pad by 2 zeros on each side to keep it at 32 by 32 by at the output activation. So as you see, that just by first of all, we can lose some things at the edges, and second of all, we often do want to downsample. We want to change the size of the next layer to be smaller. And one of the ways to do this is by using what we call stride. So stride is the distance between convolutional steps. So just to show this, we'll use a stride of 2. Okay? So now we have our 3 by 3 filter on our 7 by 7 image. Okay? And we did a convolution over here, and we got one output. But instead of moving to the next pixel, which would move from the focus over here to the focus over here, we're going to jump by 2. Okay, so we're focusing first on this one, now we're focusing on this one, and now we're going to focus on this one. So we used a stride of 2, and we got 3 outputs in the row. So now what we're going to do, instead of jump down 1, we're going to jump down and focus over here, okay, and continue. Okay. So when we finish that whole thing, and the stride better be calculated that the window covers the input nicely, we downsampled. Instead of getting our 5 by 5 output, which we got in our original example without the 0 padding, we got a 3 by 3 output. So we took this larger image and we were able to make it smaller using this hyperparameter called stride, and that is often done. Okay. So let's take an example here of calculating how many actual weights we need to store and how many MAC operations we need. So our input image is our 32 by 32 by 3 image, and we have 10 filters that are of size 5 by 5. We're going to use a stride, a simple stride that's 1, and we're not going to use 0 padding. So first question is, what is the output size? So we saw already that using a 5 by 5 filter, we're going to have 2 losses at each edge, so that's a total of 4 losses. So instead of a 32 by 32 output, we're going to have output maps that are 28 by 28 in 2-dimensional pixels, right? But we have 10 filters. So what is our output depth going to be? How many output maps are we going to have? We're going to have 10 output maps. Okay, so our final size of our next layer is 28 by 28 by 10. Okay. So how many parameters, weights, are in this layer? So again, we have 5. So how many weights do we have? We have 5 by 5 weights in each filter, and each of them has a depth of 3. So each filter is 5 by 5 by 3, and if we multiply that, it comes out 75 weights. We can't forget the bias. We have to add 1 bias for that filter, and so we get a total of 76 parameters for that filter. How many filters do we have? We said we have 10 filters. Okay, so that's a total of 760 parameters. So let's count the size of a convolutional layer. We start with a 2D W by H input feature map. Okay. And we're going to apply a convolution with an S by R filter. Each step, okay, is S by R multiplications and additions. So this S by R at any step over here has to do S by R multiplications and add them all together. Okay. The output map is size E by F, which we saw it is probably close to H by W, but it depends on the stride and the 0 padding and so forth, and the filter size. Okay, so but assuming that we are able to easily calculate this E by F, we need to do this convolution per each of these pixels. So the total size, the total number of multiplications that we're going to do is S by R, number of multiplications per 1 step, times E by F, the number of steps we actually take. The number of times we slide over the window. So that's the size, that's the number of max that we have to have for a single conv layer, a 2-dimensional conv layer with a single filter. However, we usually have more than 1 input channel. So let's say we have C input channels. So instead of R by S weights, we have R by S by C weights. So if we have E times F outputs, what we're going to have is this R by S times C times this E by F number of max. Okay, but that's not enough because we might have M filters. Okay, so instead of 1 filter that is depth C, we have M of these filters that are depth C. Okay, so now instead of R by S by C weights, we have M times M filters, so M times R by S by C weights. And that means we're going to have M times R by S by C times E times F max. So we're going to have M outputs, and each of them are going to be size E by F. So M times E by F times the size of a filter, which is R by S by C. And not only that, we often, at least our training, we do in batches. In batches, there are going to be N inputs. Okay, we have M by R by S by C weights. That means we're going to, we need to do M by R by S by C by E by F max per layer, and we have N inputs that we're going to be applying to it, and we also have to store the partial sums, which are these guys. Okay, so we have M by E by F per image, and we're going to do it on N images, so we need N by M by E by F stored partial sums or outputs. So that's quite a lot. Let's summarize this. It gets kind of complicated with all of these letters, but I'll try to put the letters on any screen that we're going to be using them. So we called n the number of input fmaps and output fmaps. That's the batch size. So if we're doing training with batches, the batch size we're going to call n. C is the number of 2D input fmaps or filters, or the channels. So C for channels. So that's the number of channels we have in the input. Okay. H and W, that's what we're going to use for height and width of the input fmap, okay, the input activations. Okay, R and S is the height and width, that's height and width of the 2D filters. So that's how many weights we have. Okay, M is the number of 2D output maps, that's the output channels. Okay, is going to be called M. And E and F is the height and width of the output map, fmap, it's the output activations. Again, E and F is going to be very similar to H and W unless we have a large stride. Okay, so we can put this all into into an equation that will, or a formula that will calculate what our each output is. So, okay, so a single output of X and Y is going to run along all E and F outputs. Okay, for the output map of batch number N and output channel number M is going to be an activation function such as ReLU. It's going to take the bias for this output channel, okay, plus a three-dimensional sum of our input times our weights, okay, and it also takes into account the stride over here. So that's a pretty there's a lot of parameters inside there. And if we want to go and make a naive 7-layer for loop implementation, we'll see we get these 7 for loops over here that are going to do this. This is our formula from above. It's actually carried out over here. Okay, then we put the activation on over here and so forth. So this is one convolution of a layer. It's pretty long. It's going to be done on a batch of n. And if we do this naively, that's going to be a real large number of operations. And so we're going to try to make some, I mean, what we're doing in this course basically is discuss how we're going to make better hardware for doing this type of a thing. So now we're going to go into the next video section and discuss the final 2 parts of our lecture.